Good morning, everybody, and welcome to this second day of briefing here at BlackHat. I am Zambon, PhD student at Twente University in Netherlands. And this briefing covered the burning theme of false positive reduction in intrusion detection system. It is the result of over 2 years of joint research between me and Zambon and Bolzoni, who is a PhD student in 22. The speech is structured as follows. We first talk about the common problems affecting network intrusion detection system, especially those related with false positives. And we then introduce a new strategy for reducing the false positive rate for intrusion detection system based on the inspection of the outbound network traffic. We then present Poseidon, that is a payload-oriented anomaly detection system that we developed as an outbound traffic validator for our architecture. And then we deal with the issues related with the correlation between the rising of an alert by the intrusion detection system and the output traffic validation. And we presented the whole high-level architecture of Aphrodite, that is our architecture for false positive reduction. And we show our benchmark that we conducted on a standard data set as well as with real network traffic. Nowadays, employed in the network intrusion detection system are usually made of a number of different sensors that are disposed on the network environment. Each sensor writes its alert and sends those alerts to some collection point where alerts can be inspected, usually manually, by the security personnel. Some research states that the number of alerts that can be raised by a single sensor can be huge, can be very large, about 15,000 per day, 15,000 alerts per day. And this research also states that the most part of these alerts are in reality illicit action and therefore are false positives. And this is a great problem for the security personnel because they have to inspect all the alerts manually in order to decide if a given alert is an attack or not. And given this great number of alerts, there is a time window between the alert is detected and a countermeasure can be disposed for a possible attack. And another bad consequence about false positive is that the security personnel can lose confidence in the reliability of the network intrusion detection system, and therefore it could decide on lowering this defense by deciding on reduce the number of checks the IDS does, and this would expose the systems. As an example of the false positive problem, here we have a simple snort rule that it is used for detecting the path traversal attacks. And this simple rule states that snort should raise an alert as soon as it finds HTTP packet containing this special character sequence //. So let's think about an HTML page published by one of the web servers monitored by the IDS sensor that has a simple IMG tag containing on the SRC attribute the // character sequence. This would imply that the intrusion detection systems north would raise an alert. But this is not an attack at all, so this is a false positive. What can be done to solve this problem? Well, we could say that tuning the IDS by introducing some exception to the rule could be the solution of the problem. But while this can be simple in this specific case, if we think to the wide number of rules that a single sensor can have, and the huge number of exceptions, different exceptions that there could be, we can see that this task is not feasible, is very hard. So tuning the IDS is very important for reducing the false positive rate, but is not the ultimate solution. Well, let's go another bit deeper into the intrusion detection system way to operate. When they usually raise an alert as soon as they find any sign of a possible attack. So what they should do instead would be to wait raising the alert until they find some kind of confirm that an attack is actually taking place. So the alert should be considered as a sort of warning, and then we should start to inspect the system and the network behavior in order to confirm that an attack is actually taking place. And this would reduce the number of false positives. Well, the question is about how can we provide such a confirm to the network intrusion detection system. And the answer is we can observe the outbound network traffic originating from the system monitored by the intrusion detection system, and this traffic could provide the confirm we need to give to the intrusion detection system for knowing that an attack is taking place. And nowadays, intrusion detection system doesn't consider at all the outbound traffic, and this just because it is very unlikely to find an attack pattern in outbound traffic. It is more likely to find attack patterns in incoming traffic. While in our opinion, outbound traffic should be considered to find out not a sign of an attack, not the attack pattern, but also the reaction to the system to this attack. And we can see this by this table in which we have a taxonomy of different kinds of attack as given by William Stellings. Attacks are classified as interruption, interception, modification, and fabrication attacks. And for interruption attacks, we have that are attacks that compromise the availability of a system. When an attacker is able to dump a system, we will observe in the outbound traffic that the communication is stopped. So there is a difference between the normal behavior of outbound traffic. While for interception attacks, that are attacks that affect the confidentiality of a system, attackers usually will try to access information the system would normally not provide. So observing the outbound traffic, we will see such information that is usually not provided by the system and that is in some way unusual. While for modification and fabrication attacks, that are attacks involving the integrity of the system, attackers are able to alter the contents of the system or to introduce new objects into the system, and these usually imply that there is an alteration on the behavior of the system itself. So this alteration will probably result in a different way to communicate, and so a different on the network, so a different outbound traffic. So in the case that attacks are not successful, we will see a difference in the output traffic too, because the system will provide some kind of error messages, and these error messages will be seen as unusual. So the idea behind our architecture for reducing the false positive is quite simple. This is to provide a way to the confirm of the attack by inspecting the outbound traffic. And for inspecting the outbound traffic, there are different approaches that we can take into account. But for instance, we can see that it is very difficult to build a database of patterns of the possible reactions to the attack. So an approach based on a sort of signature of reactions of attacks is unfeasible because each system will react in a different way for a given attack, and this just because it has different custom data on it, and just because it is configured differently for every instance of a system. So we must focus on anomaly detections, for this purpose, for detecting anomalies on the outbound traffic. And anomaly detection is more suitable because it is trained with the data, with the normal data, outbound data of the system, and then an anomaly detection system try to evaluate the traffic it observed, finding out the anomalies, and such anomalies would be considered as a reaction to the attacks. Another problem related to our architecture is about the correlation, because the problem is how can we associate the raised alerts by the network intrusion detection system with the outbound traffic evaluation. How much time have we to wait without detecting any anomaly before we can say that an alert is a false positive? And another problem is about when we do not observe any kind of response to a given alert, how do we interpret this? So we need a correlation engine that is able to talk both with the network intrusion detection system and with the output anomaly detection engine in order to relate the events and be able to confirm that an attack is taking place. And for this reason, to build the first part of our architecture, that is the output anomaly detection engine, we studied different approaches on anomaly detection system. And such anomaly detection system, these approaches are usually based on statistical models that are used to to define the normal behavior of the network environment. And to build these statistical models, different approaches use different techniques, because some approaches use the information on the header of the packets on the network, while other approaches use the information on the payload. Well, for our purposes, we can see that the payload-based approaches are more suitable because we are trying to find reaction to attacks that